Hey y'all, welcome back to the Database School podcast. I'm your host, Aaron Francis, and today we've got a crossover hit that could not be scripted any better, and the crossover is accounting and databases, my former and current loves. I actually still love accounting, just being an accountant was terrible. I hated that. But today I'm talking with the CEO of Tiger Beetle, Joran Greef, and this is the first financial transactions database. What if your database understood double entry bookkeeping? It's very interesting, and it's not just for moving money, although it is for moving money. You don't want money to show up twice, right? If you're gonna move it, you gotta move it. And so they have a lot of interesting challenges on just being extremely correct, but it's not just money. It could be credits, it could be tickets to a concert. So there's all sorts of stuff that Tiger Beetle is thinking about and handling that general purpose databases are not. And they leave all of that to the very powerful general purpose databases and focus on, hey, how do we get 1 million transactions a second in our financial database? That's the interesting stuff that we're talking about today. Before I throw it over to the main interview, I need to issue a word of thanks to you, dear listener. I moved this podcast to its own dedicated YouTube channel, which I thought was smart and a little bit of a risk, and it turns out you all came through big time and subscribed, and so I just, from the bottom of my heart, want to say thank you. Thanks for making this possible. Who knew there would be so many people that want to talk about databases or listen to me talk about databases? Goodness. So I'm very, very grateful. Enough of that. Let's talk about Tiger Beetle. Let's get to the show. We are here with Joran Greef, and he is, he's a couple things, and all of them are impressive, but let's start with, he's the creator of Tiger Beetle, he's the CEO, he's the founder. Those are kind of cool, but he is an old school accountant. He's an old school financial accountant just like me, so buckle up. We're going to talk databases and accounting. Joran, do you want to introduce yourself a little further?
Yeah, thanks, Aaron. So nice to be with you. I realize our names have got a lot in common, and you're the master of Postgres, and first time I'm up against someone, or getting to have the pleasure of chatting with someone, also in accounting. So it's really, I've been following your work, and it's been so awesome with TryHard. So yeah, really fantastic to be here.
Yeah, well, thanks for doing this. This is one of my favorite things to talk about, is a bunch of deep database stuff that I kind of know but don't super know, and so I feel like I'm going to learn a lot here today. Before we get super into it, give us the 60-second pitch on Tiger Beetle.
Okay, sure. So, database has been around like 50 years. SQL's 51 years old, general purpose for 51 years. And, a few years ago, analytics spun out, and you got all these analytics databases. And for a long time, SQL was powering the world for transactions and general purpose. And Tiger Beetle is only a transactions database. So it's not an analytics database. It's not a general purpose database. It's just the original use case for a database, which is transaction processing. So it's most databases are string databases. Tiger Beetle is not a string database. It's an integers database. So it's good for moving numbers around. It's if everything is Word, then Tiger Beetle is a little bit more Excel. So yeah, that's sort of the high level pitch. We can get more concrete, but yeah, figured the world needed a database for counting.
That last part that's a good hook. If all the other databases are Word, Tiger Beetle is Excel. That's tight. I like that a lot. So we'll dig into some of the financial stuff and some of the performance and durability and all of that. One of just as a teaser for the audience, you've got debits and credits built into a database, which is I feel so at home with that. But tell me,
you do.
Yeah, I know, okay. It's so nerdy. Back up, I guess 5 years or so, and what's the founding story? So you're looking around at databases that are very mature, very stable, very productive, and you're like, hey, I actually think there needs to be something else. Take me back to that time and tell me that story of what spawned it, and then kind of the beginning days.
Yeah, can I take us back 5,000 years, Aaron?
Sure, yeah, we got time.
So we're going to go back in time 5,000 years to the very first database, that we know of. and it had fantastic durability. So it was like the Sumerian clay tablet, you know.
It's carved in stone.
Yeah, and it's still around, you know. It's the most durable database on earth, and like there's you know, you can see it, and it's amazing because this database, it's got transactions on it. So, you know, you look at it and you see people are doing business and they're recording. You know, the trades or the transactions, like to transact is to exchange. So, you know, some good or service or, you know, or food or property, whatever, is changing hands. And then something else is changing hands too. There's money, but mostly like it's all just exchanging. And so that's what this tablet was recording. And what I find fascinating is, I only learned this recently, but this tablet existed before written language. So not only is it older than SQL, you know, SQL's forever, it's 50 years. 50 years is an eternity in technology. But this transactions database, you know, it's older than written language, and the essence of it was to express, you know, things moving between people or places. And so that's 5,000 years ago. You know, durability was a solved problem. You had transactions. The thing that you didn't have was performance, you know. So I think since then databases got a lot faster, and so Tiger Beetle story is pretty similar. You know, 50 years ago we had a great general purpose database, used it for transactions, like we said. Durability was pretty good, and then the thing is, in the last 50 years, you know, even the last 10 years with the internet. The world's become a lot more transactional, so things are moving faster. People are transacting more, and they tend to transact now with higher resolution. Like your TV has been the same size, but the pixels got smaller, and so around the world, you know, transactions are getting smaller. So that you can supply and demand can meet more frequently. People can exchange in more convenient quantities. And what that means for the underlying databases is that the volumes are going up. So there's multiple sectors, you know, energy, they're trading kilowatt hours. Uber is matching drivers to ride sharers. You know, cars are becoming more transactional. You used to rent a car, now you just rent a driver, and you rent a driver 5 times a day. And then Airbnb is the same thing. And music, you know, you could buy an album, then you could buy a song for 99 cents, and now no one does that anymore. You just stream. And cloud was the same thing, so it became more transactional. You'd buy a Dell, you know, stick it in a rack for 3 years. Then you would like rent with Hetzner, and we all still do that. But you can also now just do serverless and per second billing. And now you're getting machinery, but very transactional. So here's the question, you know, how do you account for all of these transactions as they get smaller and more frequent, and there's more of them? And what that means is the last 10 years, there's maybe in some sectors, you know, 2-order magnitude increase in volume, 3-order magnitude. In some sectors, like instant payments, it's 4 orders, which is actually 10,000 time increase in 7 to 10 years. So that was UPI, their real-time payments has gone up literally 10,000x. Pix is another one of these. FedNow is coming to the US. So, you know, I think all of us, we're tapping our phone more and more, transactions behind the scene. And the problem is, for 50 years, a general purpose, like we call it OLGP, was pretty good. You know, you could use it for analytics. But a few years ago, the analytics people said, well, actually, we think we need to go from row major format in the database storage engine to column major. That's going to give us better analytics performance. And so you've got DuckDB and analytics databases. And so the general purpose database is not really, no one would say that Postgres is an OLAP database. It's a general purpose database. And yes, I think most people would say use it for transaction processing as well, you know, whatever that is, and we should get to debit credit. But the thing is, yeah, with this big increase in transactions volume, it's actually at the point now where you know, the 30-year-old general purpose database was not designed for this volume of sheer numbers coming in and flowing through. And there's sort of some fundamental limits, like Amdahl's law, we can get into, like why that is. But Yeah. Anything that you want to double click on there, or that I can fill out a bit more?
Yeah, definitely. I mean, that was a concise history of the past 5,000 years. You did a great job there. So I guess my question is, or to synthesize it, it sounds like you had one of those early Jeff Bezos moments where Jeff Bezos looked at the internet, said, "This is coming. What can I sell? Books. Let's start with books." On the other hand, you looked and said, transactions are getting smaller but more frequent, and that is fundamentally a different workload than I go and buy a car and we put one row in the database that, maybe two that says transfer from this person to this person. Now we're putting, hundreds of rows in the database just for me, just for a day.
That's
and
it.
So you're looking forward to this future where the world is changing, commerce is changing, and the old databases or the existing databases are great, but not necessarily built for this micro transaction environment. So you're looking around and you're seeing all of this change. And so what is your, where were you at that time? Where were you working? What were you doing? And what did you decide in that moment? How are you going to go and build something that is, the Excel versus the Word? What was the technological insight that you had?
Yes. Thanks. That's such a succinct summary. And, I love how you said, it's the bookstore meets the internet. And because that's exactly what it is. Because, and I should say, general purpose is really excellent. And everyone is on Postgres, and it's excellent for general purpose. Mm-hmm. And it's excellent. If you were starting a bookstore, in our back in the garage. General purpose would be brilliant for what are the names of the books, the authors, the comments, the reviews, all the strings, the customer names, addresses, and a lot of that information doesn't change very often. It's like reference data. You put it in. It's like filing cabinet data. You put it into the database, doesn't change too much. You tend to read and query it a lot. So, SQL is a great language to get information out of a database. And yes, you use it to put it in as well. But this general purpose data doesn't really change too much, customer's name, password, but it's very general. But the bookstore, the thing that it struggles to scale on Black Friday, it's not the password changes or the addresses. Mm-hmm. It's not the names of the books or the colors of the car if they're all black, The thing that it struggles to scale, and you know this, is it's updating the counts of what's in our warehouse, what's on the trucks, mm-hmm. what's in the shopping cart, and for how long, and when does that shopping cart expire, and those numbers must move back again. Or maybe, yes, the checkout succeeds, and now we record that, and there's a tip, and there's fees for partners. And so that's the volume of Black Friday, all these numbers. And so, so I guess I should get to, where we're going here, but where was I? And I'd never worked in payments or commerce, or I wasn't in that world. So I'd always been in distributed systems and storage systems. It was my passion and hobby. And I'd been coding, started coding when I was 11. So that was 30 years ago. It was QBasic for me. Then it was PHP, Ruby, Java, VB, I don't know how much we intersect, but definitely.
PHP. So we've got
Laravel.
3 things in common. We've got PHP, accounting, and databases. So we're the same person. And so that was you grew up with the web and even Netscape, and you had the modems in the wetsuit, and but anyway, so that was my journey as a coder, and then it ended off me doing a lot of performance work and algorithms and fast software and storage systems, file systems, distributed systems. I knew nothing about payments, and until 2020, and it was COVID, and I bumped into people in California, and they asked me to come and work as a contractor on it's a central bank payment switch. It's non-profit,
foundation. It's set up by the Bill and Melinda Gates Foundation. It's called Mojaloop, and it's an open source payment switch. And there's about 20 countries around the world where they are now deploying this with the idea behind it is it's very similar to what we were speaking about, UPI and PIX, is that you can start to make payments cheaper for people by making them smaller and more frequent. So people could transact on their phones. They don't need bank accounts anymore. Fees go down. This is the idea. That's why it's a nonprofit. So I was asked to come and see how can we make this system faster, because the more performance you have, the more it can actually make a little bit of a dent. The fees drop because it gets cheaper to process transactions. There's less. You don't have these 20 cent or 2% fees. Those fall away. And for some people in the world, if you can say, some people are paying way more on fees, 5-10%, and then the fixed costs, they also are dealing in much smaller transactions than you or I are used to. So to them, this means a lot. If you can reduce their fees, they start to save, and a lot of people start to move above the critical poverty line even. That was why the Gates Foundation started this, because these things compound. You save someone 10% each transaction, changes. So I really liked coming into the system. It was open source, and I loved it because I was paid to make this thing faster is my passion, and it's open source, and I knew nothing about it. So I had a lot to learn, And the thing that I learned that surprised me the most was having done a lot of performance work. Usually the CPU is on fire, and then you're looking at flame graphs, or the disk, you need more IOPS, you need to go bare metal, you need to go NVMe. Or there's not enough RAM, or the network link. So usually it's we call them a Tiger Beetle 4 primary colors: network, storage, memory, compute. They've got 2 textures. If you want to paint with them, they've got textures of bandwidth and latency. You got 4 colors, and that's how you can sketch fast systems from first principles: network, storage, memory, compute, 2 textures, bandwidth, latency, and you can do a lot of performance work in terms of these. And the conundrum for me was looking at the central bank payment switch, to power a country and change things, make things cheaper, drop fees. We just couldn't make this thing faster than 78 transactions per second. And I thought, this doesn't add up. Postgres can do 12,000 of these row movements, transactions between 2 rows, between Alice and Bob's row. You can do 12,000 a second. And we couldn't do 78. And I thought, this is very odd. So the first thing I did was I said, okay, let's give it NVMe. Let's go because this was 5 years ago, let's give it NVMe. And the system didn't get faster. And we could see that it was waiting on the database. But then you look at the database machine and you let's give it more CPU. But the CPU is idle. The network is not a problem. And there's plenty of disk bandwidth, plenty of memory. So the weird thing was nothing was moving, and the database was the bottleneck, and we couldn't make it go faster. And then this was when I started to learn something about transaction processing, because people who had, someone, my manager I was really fortunate, Adrian Hope Bailey. He was the co-chair for the web, the W3C web payments group. MasterCard were there, and Visa, and all the tech companies, and Adrian was the co-chair, and he'd been at SEI and Postillion and all these payment systems his whole life, and people like Adrian said to me, Joran, it's the Rolex. If you take a SQL database and use it to transaction processing, like general purpose database for transactions, you're trying to do, if you look at the Postgres docs, I love how Postgres for transactions, the example it gives you is Alice and Bob. It's right there. It's the heart of Postgres as SQL transactions is, how does Alice pay Bob if you're a bank? And if you do that with Postgres, what will happen is you'll begin transaction, you do a query to the database, you ask the database, get me Alice and Bob, and then you get it back to the app, and it's general purpose. So in the app, you go, okay, is our logic okay? Does Alice have enough money to pay Bob? okay, let's do this transaction. Let's send another. Let's do it. Send it in, and then we send a commit. So you have like typically 2 SQL queries at least, while holding locks on Alice and Bob. And so that's what was happening in this switch is you had a few queries to do a real world transaction holding row locks across the network. And if you look at those 2 things, network round trip times are constant because speed of light in fiber doesn't change. The best you get them down to between AZs is like 1 millisecond. And that's it. So you're holding row locks, for 1 millisecond per transaction. There's 1,000 milliseconds in a second. So if you have 100%, if all your transactions are between Alice and Bob, everybody is queuing up on those 2 rows. You've got 100% contention. The most TPS you can do is, is like 1,000 per second. But that's theoretically. And in practice, like you burn that up fast and you get to about 100 a second. And that's just the Amdahl's law. Amdahl's law is imagine your system is infinitely horizontally scalable. You got 10 billion machines in your horizontally scaled database. Amdahl's law says that the throughput is going to be dominated by the sequential portion of the work. In other words, by your serializable transactions. And so actually with OLTP, you're looking at 100 TPS, maybe 1,000, but that's, yeah. So that's where I was, that's what I discovered. And I guess we come to Tiger Beetle and looking at that system, I was consulting, but it wasn't my normal work to be a consultant. I only did it because I thought it was interesting work. Otherwise, I wouldn't have done it. I had my own, company at the time and did a lot of open source work. But I looked at the system and I thought, I could spend a year or 2 tuning the database and maybe we get 1% faster, 10% faster. I thought, storage systems, distributed systems, this is my hobby, my passion for years, reading all the research papers. The world's changed a lot in 50 years. How you design a database today, the 4 primary colors, network, storage, memory, compute, the bandwidths have actually all inverted. So long ago you had a Linux scheduler and you would burn your memory bandwidth because disks are slow. And you'd burn your memory bandwidth because disks are slow and don't have enough IOPS and you want to keep stuff cached. And you'd construct Bloom filters in memory and burn your memory bandwidth again and thrash your CPU cache for the same reason, But these days, disk bandwidth is overtaking memory bandwidth, and so is network. So actually, gravity is kind of inverted, and the whole way you design a whole database is totally different. So. Yeah, I guess you should stop me, Aaron. But this was kind of getting to that moment where you think maybe we could, in a year, maybe we could build a database.
So I don't want to stop you because it's a fascinating story. And so for the audience, I think one of the interesting things about the line of work you're in is, what the line you were in at the time and still are in, is this financial transactions thing. And I think the most important thing that a bank does is make sure that the money goes one place and not 2. And actually not 0, right? You don't want to remove it from, Alice's account and it goes nowhere, but you also don't want it to end up in both people's account, right?
And hopefully at the same time too, so that it doesn't leave your account and not arrive or arrive, but it's still in the other place.
It can't end up in the ether. Yeah. So that tablet that you were talking about 5,000 years ago, did that have debits and credits on it? And if so, I will explain debits and credits very quickly.
Yeah. So I think
it did, right?
It maybe did. I think it was more single entry, not double entry. So it had the count, but it didn't show. It didn't have the vector. So it didn't show from Alice to Bob. It was more like it was 10 units of barley. And you could see the drawing of the barley and see how much, but it didn't show you the trajectory. It didn't show you that you're taking an Uber trip from Newark to Manhattan. It didn't have that vector in it. Yeah.
All right, so y'all are in for a treat because I'm about to just very briefly explain double entry accounting, which is a delight. If you listen, if you haven't,
Aaron, please, this is so awesome for me. I'm just going to sit back and enjoy this.
So if y'all haven't studied financial accounting, so there's, of course, like managerial accounting, which is a lot of internal stuff. That's a little more loosey-goosey. Financial accounting is very rigid. It's very similar to programming. It is logical. It has rules. There are like 4 rules, and if you just apply the 4 rules over and over and over, everything balances out, and now you're an accountant, right? And so I fell in love with accounting in college. That's what I got my degree and my master's in, and I spent a year as an accountant, and it turns out it's more fun in theory than it is in practice, but the theory is very interesting. So the thing I want to get to is that you have built a database with double entry accounting. And so backing up, what is double entry accounting? Basically, in accounting, you open up all of these accounts, these charts inside your business. You've got cash, you've got equipment, you've got revenue, you've got expenses. And all of these accounts have have 2 sides. They have a normal side and they have an opposite side, right? And so when you spend cash, you write down 2 entries. You say, I spent $200 of cash, and you decrease the cash account, and then you increase the expense account. And so there's always 2 entries that go in to say cash went down, expenses went up. Cash went down, assets went up. Wherever the cash goes, revenue goes up, cash goes up, right? And so this is fundamental. This is super fundamental to accounting because at the end of the day, everything balances out.
It's like one of those Newton laws, money cannot be created nor destroyed, but merely moves from one person or place to another. It doesn't. It doesn't just disappear because then it's theft.
Exactly right. And there's actually an account for that. There's an account called shrinkage where you're like, well, it's gone. We'll just have to credit the shrinkage account because it's gone, right, or debit it or whatever. So
otherwise, the universe will collapse.
Yes, exactly. And your auditors will be very mad at you. So, so this is a fundamental part of business, is this double entry accounting. And so you're looking at these databases and saying they're really good for general purpose. They don't meet this. They don't meet this double entry accounting. They don't meet this integers. They're all strings instead. And so I want to get to the part where you build a database that is integer based instead of string based, and how are you building in this fundamental law of business, which is double entry accounting? So start with this structure of all right, we're going to build a database that's not based around strings, it's based around integers instead. And what was where did you start with that?
Okay, great. Yeah. So I love your explanation. It's so good because I didn't do my master's. I got my undergrad. It was my major, but I didn't do master's. I got into coding.
You're a smart man.
Or no, well, you too. You got into coding.
Eventually, yeah.
Eventually coding, and but I think what I also love about debit credit is accounting could be financial accounting. It could also just be accounting and just debit credit. So it doesn't have to be money. It could just be units of barley. But also the debit credit, it's also the world's oldest type system. So if you love type systems, a debit credit is like a type system. So in the financial accounting world, you have 5 types. Essentially, if you think of all the different accounts you have, like what you took us through now, the bank account is the type of the bank account is an asset. And the asset type increases on the debit side. So that's all you need to know. If the type is an asset, it'll increase on the debit side. Imagine the account has got 2 columns. That's why they call it a T account. It's literally the simplest table. On the one side, on the left side is debits, and you just add numbers. It's like a running total, like you're scoring Scrabble or something. You score for player A on the left, that's debits. If player B does well, then you score on the right, which is credits. But the asset type increases with a debit. A liability type is when you owe somebody else. Asset is when they owe you or you own something. and liabilities increase with the credit. Equity is your ownership in a business, and then the other two are income type increases on the credit side and expense increases on the debit side, and that's the type system. So when you know that, like let's say I'm buying a car, that's an asset. It's going to go up player A side on the debit side, and to buy a car, I either had to pay cash from my other asset, from my bank account. So I'm going to decrease that asset and increase another one. So it's an exchange. I'm exchanging my asset for somebody else's asset. Or if I didn't pay cash, I took a loan, then it's going to be a liability type. And then you can name these accounts anything you like, so it could be bank account or my loan with this person or my loan with my parents or someone else or my friends, my angel investment for my car, etc. But that's the type system from a financial perspective. But getting into Tiger Beetle as a database, what does it look like? So you have two things. You have two objects. You have accounts. Accounts are these T's. And then you have the actual debit credit, or we call it a transfer, which is the movement from one account to another. So you're debiting one account, crediting another. And you're always doing both. You might, for certain transactions, might debit this account, credit another, debit this and another. And you can actually stack a whole lot of these and express a whole lot of real world contracts or, product experiences like that. So, move the good to my shopping cart, pay for all the goods, do the delivery, do the logistics, move units in the warehouse onto the truck. And that could all be a whole lot of debit credits denominated in different units of value or currencies or assets. Or
okay, can I pause you there for one second?
Let's pause. Yeah.
So what you're describing to me sounds like very traditional accounting, which is you have point in time, which is like accounts that says like this is the the cash balance or whatever, and then you have what we would call like a journal or a ledger of like things that have happened, the events. I guess in
events,
programming world you'd call it events and event sourcing. But is that kind of what you're describing? You've got
that's exactly
point in time accounts and then the running ledger of things that have happened that affect those accounts. Is that accurate?
That's exactly it. So if you think of a SQL database, you've got an accounts table with two rows, a row for Alice and for Bob. The ID for both of them. You also have their bank, their balance for each of them. And the only difference is that instead of just, when you move the money between the two of them, you do that. But now you have a separate table called like transactions, which is your events. And now like the debit credit is capturing a bit more information. So in this transfer or transaction, which represents a real world transactions, because that's where we get the name SQL transaction from. It was originally to model these kinds of things. For the first databases, the lineage was, banking, brokerages, warehouses, inventory, airlines, ticketing, logistics. These were the use cases for SQL transactions. And so, but if you look at this transaction object in your transactions table, you have a timestamp for when it happened, when. You also have the debit account ID, the credit account ID. These are just numbers as well. You have the amount. It's also an integer. That integer, you can then scale it with decimals after the fact, because you'll also have another number that tells you the unit of value. So are we transacting kilowatt hours or dollars or cents or, am I transacting a ride in my car, or is it a room in an Airbnb? These are all units of value. So that's another number. So how much of what? So it's what, how much, when, between who, or from where to where. So, and this is sort of the essential information of debit credit, which is centuries old. It's been more than just only the accounts table where you only have one number for Alice and one for Bob. That's single entry, because now you're just moving numbers, but you've got no history, you've got no event sourcing. Right. And event sourcing is great. So, and accounting has always had that. So you have the second transactions table, which has the who, what, when, where, why, and how much of debit credit. So that's all just numbers, very boring. But with this is like the perfect schema. It's like it's the essential, if you could do 1 million SQL migrations to get you to the most universal like SQL table schema format in your Postgres for modeling Amazon or some cloud billing or some startup API usage or kilowatt hours or whatever, this is all you need. With these primitives, they're so simple, they're not inflexible, they're actually highly composable, because they're great building blocks.
Yeah, so this is,
I think
this. This does sound like the platonic ideal, the ideal state of a generic system, which is why it's survived for as many thousands of years as it has. So what you're describing so far sounds to me like something that is creatable in Postgres, SQLite, MySQL. So what is the difference between building it on top of this general purpose database, any of the three I just listed, and is it like a first class citizen? Is it something different than just like a table? Like where does it break with Tiger Beetle off of the lineage of old general purpose databases such that this system is built in for performance?
Yeah, absolutely. Yeah, for performance. So that's the reason why you can obviously model all this with you could construct these primitives with OLGP, just like it's kind of similar to Redis, all the primitives in Redis, yes, you could go and implement those over Postgres, the sets and all of those, the awesome stuff that anti-rest put in. That was also my way into databases, was watching him craft Redis and how that love of crafting and C99 and code is poetry, reading his essays. Like that was the first time I saw an append-only log and realized this is the heart of a database, and so that was my journey in. But like Redis has got all these primitives, yes, you could express them in Postgres, but probably going to be a lot faster because Redis optimizes for it. So in the same way, you could do it with a general purpose. The problem is the locks. General purpose is going to hold row locks across the network round trip. And the other insight that I learned from these payments people was that with transaction processing, as you build an app and your app becomes popular, like you start to attract the power users. So if you're like a ticketing app that becomes popular, at some point Oasis are going to book their 24 tour through you. Because you reach the scale that you attract the power users. So like Oasis said to you, right, we're gonna sell our tickets, 1.4 million tickets. I think it was 1.7 million last year. So I can't remember what it was exactly. Maybe it's maybe a bit higher, a bit lower. But what I do remember is there were 14 million people that rocked up to buy tickets. So they're all saying begin transaction and Rolex. 14 million. Wow. And you can imagine like it crashed the OLGP database because everything is just locked. and so you're doing 76 a second and because it's Amdahl's law and you just can't do it because there's 90% of your transactions are going through one row, which is the Oasis row. So you cannot scale it. You can't horizontally scale it. You can't vertically scale it. And if you look at this, the same problem I saw. You look at that database, it's crashing because of Oasis, but you can't give it more RAM, you can't give it more NVMe, because all the resources are literally, it's like Spider-Man spun a lot of web across your network and took locks. And that, so the way to make it go faster, what we did for Tiger Beetle is we said, right, what you're really trying to do is give people some tickets. Let's debit Oasis's supply of tickets or credit their supply of tickets and debit the lucky buyer, who bought a ticket. Let's do a lot of that. And the essential information is like 128 bytes. It can fit in 2 CPU cache lines. Again, it's the when, where, why, how much of transaction processing, the debit credit. And that's 128 bytes. So, if you imagine like you've got your database for your ticket site, and then you've got like a few stateless API instances like gateways around like 3-tier architecture. Okay. And the users are pounding that, but you can scale that stateless layer. They're talking to your database, but each API instance is like being pounded. It's got like 1,000 people. So you say, okay, no problem. Let's take these 1,000 debit credit requests. let's just pack them together. Actually, let's do 10,000. That's only 1 megabyte. It's literally a 1 megabyte, buffer of information for 10,000 people that want to buy a ticket. 10,000 debit credits, 1 megabyte. Let's make our database query interface first class debit credit and just send a 1 megabyte query with 10,000. The database can write that to disk to the append-only log fsync once. It's literally doing like one receive call from the network socket, one write to disk, one fsync. It's beautifully amortizing all these costs and just pushing them through the state machine, with the LSM storage engine, all of that stuff that databases have. But it can amortize, and it's not holding locks across the network. And then it comes back to you, and you're like, we did 10,000. Now it's very easy to do 1 million a second. Because you just don't have that limit anymore. So that's actually Tiger Beetle. That's the key to Tiger Beetle's performance, is to say, what is the essence of transaction processing? It's always been debit credit, something moving from a personal place to another, this vector. There's a magnitude, it's all integers, and all the general purpose information, what is OAS's name? What is their bank account? What is their address? Who are the people buying these tickets? That information is in your general purpose, and that's easy to scale. So now you have very nice separation of concerns. You have your general purpose filing cabinet and all the money in the bank vault, and that's how Tiger Beetle does the performance. But you also get a very nice architecture, and it guides you, I think, into how to just get it right. And with performance. So you actually do get, we say 1,000x, but with some systems you actually get a bit more. You can get like 2,000x in practice, because a lot of systems can only do 27 a second because they tend to do more queries. So it's actually not that hard to go faster if you could use a string database for counting, for arithmetic. And obviously you can express integers in Postgres. It's just that it was never designed, to handle like 90% contention, these power law users, Pareto principle, 90% of trades are by 10% of entities.
So help me understand, you're talking about these API servers that are getting hammered, and instead of sending onesie twosies across the wire, you're compressing it, you're batching it up into these 10,000, these 1 megabyte chunks, and then sending that to Tiger Beetle. So where is that pooling happening? Who is responsible for it? And then what are we sending over the wire to Tiger Beetle? Is it shaped like a SQL query? Is it something fundamentally different? Do we have control over how big the batches are? Talk me through the logistics of, I'm an application developer working on the API.
Yeah.
What am I doing? What am I thinking about?
Yeah, sure. So you say you're in Node.js, you go npm install Tiger Beetle client, Tiger Beetle node. Then in JavaScript, you say Tiger Beetle client, create transfers, and you can just put one in, just one, and you'll get a callback. And the database client driver under the hood, if that's all you've given it, it's going to send it off immediately. So you're not paying for batching latency. Sends off that one debit credit immediately. If another one or two come in from concurrently in Node.js, you get another one. Then the client driver will automatically batch them internally. And when the other one comes back, it'll send off now two. So as you start scaling, the batches fill up, but you never pay for that latency. And when you're dealing with full batches, you're starting to get better latency and throughput. So it sort of follows a U curve. Because you're getting more performance, your latency doesn't spike because everything's locked. You get better latency as you get the sweet spot of batching, and then yes, at some point your latency goes up. But we've tuned it at around 8,190 debit credits per query, and there you're looking at like a P99 of around 20 milliseconds. So in 20 milliseconds, you can execute 8,000, and you're like, it's nice, it's fast, but you're getting high throughput, low latency.
Yeah.
And what does that look like on the wire? So it doesn't need to be SQL, because SQL is a great query language. But this is the other thing, general purpose and OLAP are all about getting data most of the time, getting it out of the database and in interesting ways. Transaction processing it's not trying to do scuba diving in your data lake. It's trying to just fill the dam, you use the firemen bringing the hoses, and they're just trying to let's put as much water in as quickly as possible. It's very boring. So the queries are very routine. Like, let's just get the data, the business data in, and then yes, we can do all the general purpose reporting query stuff, out of our data lakes. So for Tiger Beetle, you don't need SQL, like the serialization of strings. It's all numbers. So literally what we're doing on the wire, it's all cache line aligned, fixed size structs, zero deserialization. Because again, how you do a database today, memory bandwidth is the bottleneck. So you don't want to spend 10% of performance on JSON serialization, because you're just burning memory bandwidth, you're thrashing the CPU cache. L1, L2, L3 is just, you don't want to do that. So it's really like what we do. The client does all the work, because you can scale your API servers around Tiger Beetle. That's easy, stateless. So the clients are going to pack it in a 1 meg format. It's literally, you can look at our transfer struct in the docs, and you see, there's like a fixed size ID, 128-bit, 64-bit timestamp, and literally it's a fixed size struct. What's on the wire is exactly... there were some old NTP systems that did this trick, where it's zero deserialization. So with Zig, that's the language we chose, because it's just great at this kind of stuff. You can bytecast what comes. We obviously use checksums to check that the format's correct. But then you literally just point your pointer, first-class pointers. You don't have to waste cycles on deserializing. And that format that comes off the wire is exactly what goes to disk as well. So you don't have to, everything is just streamlined for, like 4 syscalls, minimum of we try to do zero copy all the way through. So when we write to disk, we're not copying buffers. We literally take the incoming network message and we zero copy with direct IO straight to disk, trying to save memory bandwidth. These are not the 1000x performance ideas. These give you like 5% here, 10% here. But again, because this changes things for people, like it's worth it, So, and it's simpler, easier, fun. So that's how we did Tiger Beetle. Yeah.
So it sounds to me like because of the I'll say limitations, but maybe better is like narrow scope. Because of the narrow scope of what Tiger Beetle is like built to do, you're able to give more power to the clients. And so the client, which, like you said, is scalable. You can spin up, 1,000 API servers with the push of a AWS button.
Yeah.
You can farm out some of that work to the clients, and then those can scale up and down quite nicely. And then they send across the wire the distilled, like, most high value packets possible that you can then take and then just like basically slam into the database without having to like take a string that comes across and the parameters that come across and like bind them all in and then turn that into something and then run it. And so this is a very clever, I think this is one of the things that you probably gain from being so narrow in scope, is you get these kind of enhancements. And so I guess talk to me about you may have said this, but this is all very, very deep for me. So it's a little over my head, but talk to me about so you've got, whatever you said, 8,000 ticket like reservations basically coming through, ticket transactions. And so it's like, hey, I am Aaron, I'm ID 2. and let's take it out of, ID1, which is Oasis, me and Oasis, the only people in the database. But then what do you like? So you slam those into the journal or the log or the ledger, whatever people want to call it. Who or when are you going to like update Aaron's account and Oasis's account? Because it feels like that would be contentious, right? So even though you're getting these 8,000 across the wire all at once, you still got to go touch the Oasis row. I guess you can do it one time for 8,000. Talk to me about like the actual chart of accounts and who updates that.
Yeah, great. That's so nice to go there next. So the thing that kills OLGP is the contention across the network, specifically because the network round trip time is a constant. That it'll never, the speed of light in fiber, will always be 2/3 of the speed of light. And so that is a constant. The performance of the system is a function of your network round trip time and the contention of your workload. Those two numbers you can plug into Amdahl's law and you'll get your limit. And the thing with what is actually interesting, I think this is what I only realized this year, is that if you have a typical, and we'll get to the question, but if you have a typical, say, Postgres database, and you have your clients, and they're all in, New York City, and that's where your server is, it's all good because you don't have much network round trip. But if you're like SRE suddenly spins up a job, in California, and starts doing transactions, and you've got some contention, you might just see your whole system throughput slam. Because and it's a very weird effect. I never knew this was possible until like really thinking about it this year. But Tiger Beetle still has the problem of contention internally. So how do we do that? And the answer is that you're getting these nice messages of 1 meg. And so what Postgres would normally do, or OLGP, the concurrency control. So Tiger Beetle is a whole database internally. We have a whole like brand new LSM engine, a whole lot of ideas from research there. It also has a consensus protocol. It's also doing full-on, replication and automated failover, and the same things benefit from this amortization. But let's talk about concurrency control. So Postgres, if you gave it, Postgres is doing group commit internally on the order of like 16 things. I don't, MySQL, they're somewhere around there. I don't know exactly. You will know, Aaron, what it is. But let's say it's 10 or 100 things that get batched up, and then Postgres will f-sync that and apply it. The thing is, though, when it serializes the transactions, because you have to use serializable, you can't use read commit at the default, because that would give you the wrong numbers. So you have to serialize them because you want to make sure you don't oversell tickets. So Postgres will say, okay, yeah, let's do the first debit credit of 8,000. Let's say like we tune the group commit, so we are doing 8,000. Postgres is going to take the first one, read Alice, read Noel, or read the Gallagher brothers. And now you got the two accounts. It's going to update them, write them back, also write the transfer event. Next ticket, okay, read Noel or read the Gallagher brothers and read Bob. Do the same. And each time you're just reading and writing Oasis up and down, up and down, up and down. So what Tiger Beetle does is we've got this buffer in memory of 8,000 ticket orders. Then we can see that 90% of these are touching the Gallagher brothers. And then the other side is it's high cardinality. So one side of the debit credit is low cardinality. It's only Oasis. The other side's high cardinality. So let's load the Oasis brothers once, their account, and then let's go and bring all the other accounts into memory. So we do our IO and concurrency control once, and we amortize that. And then once you've got the accounts in memory, you're just like, let's push them through, which is hot in the CPU instruction cache. Just update all the numbers, do the business logic. Are we exceeding our debits, exceeding credits? So Tiger Beetle gives you a whole lot of primitives around debit credit. There's quite a lot of cool stuff you can do. So in other words, it's taking one lock across 8,000, but CPU time. And then at the end of that, it says like, right, we updated Oasis account 8,000 times. Here's the result. Let's write that to disk. But back to your earlier question, the Alice and Bob and them are seeing the ticket quantities they're adjusting in real time. So now you're able to express transaction processing logic with real-time visibility into what, how much back to the bookstore, how many books are on the trucks or in this warehouse or delivered or refunded or returned, ratings, and like everything is in real time now, whereas most systems can't do it in real time anymore because of the performance. So they started all this complexity. They use like time series database, and half an hour later they will go and figure out, but they're not able to know in real time. So this is the other benefit.
Something that is of primary importance is you don't oversell. You don't over withdraw, you don't oversell, you don't overcommit a house to 2 Airbnbers, right? And so you can't have a process by which you run 8,000 events and then you roll it up. Even a second later, a second later, it's too late. There were only 4,000 and you ran 8 and now you're host. And so this is another, I think, interesting benefit of being so scoped down, is that you can do these performance enhancements where you're like, listen, I have 8,000 transactions. Let me take a look at them, see if there's a commonality here, and grab those, and then we can just power through those super fast. And when we reach the end, we'll write it back to disk, and somebody else can come along and run another 8,000. Is that kind of like the whole idea of Tiger Beetle? Is that like we scope it down and then we can do these massive improvements?
It's just simple and standardized, and the nice thing is exactly that, right, as you've described it. And what's also nice is you get very strong invariance because the database is enforcing it now as well. So you're not just getting row column consistency. The C in ACID is about, are we enforcing application invariance correctly? And isolation is like things like serializable or strict serializability, etc. But you're getting very, very strong semantics because you're getting the guarantee that money cannot be created nor destroyed. And Tiger Beetle does the checks for you, the balance checks. So all you have to do as the application is you express these nice contracts, and you can even do debit credits that are like back to back. So you can say, right, we want to do this contract where we're going to debit credit to do Oasis tickets, and we're going to book a Uber ride, different units of value, and we're going to do this, this, and this, and this, and this, and all these things. But if one of these fails, then don't do any of them. So you've got like debit credit atomicity across transactions in a way that with OLGP, yes, you can do one debit credit with multiple queries in a transaction, but you can't really express transactions of transactions in the same way. So it's much more complicated because you don't have the same. Tiger Beetle is actually like a higher level of abstraction, and but it really, it does make these things. You could build Ticketmaster that can never crash in a weekend, and it'll nice, huh? Yeah, and you could really do the Oasis tests. It would be cool if someone could build this, because it would work. It'd be so simple. So or airline reservations, etc. Yeah.
So everything you've described so far is like mission critical. We're talking money, we're talking tickets to the biggest shows on earth. Like all of this is super mission critical. And so that feels to me like, boy, that's a lot of pressure. I think one of the things that I have read about y'all is your resilience against storage faults. And so talk to me about if you're moving money around, if you're selling tickets to the biggest show on earth, you can't F it up, even if it's not your fault, right? Even if it's not your fault. So what are some of those resiliencies that you put in place for things that aren't your fault, but at the end of the day, they are your problem?
Yeah. So, that's sort of what I realized, working on that central bank switch with the Gates Foundation is like, there is no ways that a country, so like it's been publicly announced, but this switch is going to be powering Rwanda's national digital payment system 2.0. Wow. Like the whole country will be running on this system, and this system is currently integrating Tiger Beetle, and so there's just like, but 5 years ago when I had this a little bit idea, I thought, let me write a proposal that we will, because I could do a year of work and we go 1% faster because of Amdahl's law, and that's fundamental. You can't break physics. Or I put a year and I'm And I had to write the proposal a few times before people believed me, or they did believe me, but it was like a question of the time. How long will this take? Mm-hmm. And so I realized, but the thing is that, Oracle is 50 years old as a database. It's a year younger than SQL. SQL's 51 years this year, Oracle's 50. And the advantage of technology is it moves in waves. So, just like performance has changed, the way you would design a database today for performance has changed for transaction processing. For OLGP, it's still perfect. For OLAP, of course, there's all new stuff. But for OLTP, things have just totally changed. The way you would design a database for safety today has also changed. So Foundation DB sort of pioneered this deterministic simulation testing. So you abstract away your software in a way that you can simulate the disk, the network, the process crashes. Everything is simulated, all the faults, and you generate this world from a random number generator, kind of like Scorched Earth or Worms, those procedurally generated game levels. And then you do a whole lot of fault injection, and if you find bugs, you can replay and fix deterministically, but you can also fast forward time because you've made time deterministic. So now, instead of waiting 2 years to find the 2-year bug, you can speed up time and run it in a while true loop, your clock. And so you start to find bugs much faster ahead of production incidents. But to do this, you have to design the database from the ground up to run in like a flight simulator. So it's kind of like, in the past, it was like, how do you build a Boeing? Well, you build the real thing and then people go and crash it many times. Today, it's like, well, no, you train the pilot in a flight simulator, but databases have kind of had the same moment. And so actually, you can build much safer databases today if you design them like Foundation DB or like how we did for Tiger Beetle. The other thing is, so that's the testing techniques that we used. And like you said, with storage faults, when Postgres came out, same time as Windows 95, it was 96 for Postgres. MySQL was 1995, and we all run Windows 95 today. Postgres was a year after 96, and Postgres is a phenomenal database, of course. It is the standard for OLGP, and that's not changing. That's the interface. But 1996 was a long time ago in research. So how do you build a storage engine for transaction processing? Today, the ultimate is an LSM tree for optimizing writes. And that didn't exist. That paper came out the same time as Postgres. So that research didn't exist. So how do you, do disks fail? In those days, no one understood that. And today, there's a lot of research. Most of it actually was recent, 2018, like fsyncgate, showing how MySQL, SQLite, Postgres can have data loss if a disk fails because the kernel page cache can get incoherent. There's a paper called Can Applications Recover from Fsync Failure? That came out 2 years after fsyncgate 2020, and it showed that the fixes that MySQL, Postgres, SQLite did are actually not correct, and they're still not correct. So Postgres is busy merging direct I/O. I think it might already be in. And then there's a few more things, and then it might be starting to be correct for fsyncgate. But there's a lot of research like around storage faults and also for distributed systems. So a long time people thought that if you just have replication in a distributed database, redundancy will give you fault tolerance if your disks partially fail. And then also 2018, another, this paper, Protocol-Aware Recovery for Consensus-Based Storage, won Best Paper Fast. They saw that actually most of our distributed systems, Kafka, etc., and most of the distributed databases, they all have a very similar, they use a replicated state machine architecture. And this architecture is fundamentally broken. And in a way that if you have a single sector fault on one disk, on one machine, it can propagate through consensus protocols like Raft or Paxos. It can propagate and lead to split brain and global cluster data loss. That was the finding of the paper. So that was like, fsyncgate we found in the wild, like Craig Ringer reported it, and it affected most databases. Protocol-aware recovery they found in research, and that there's a few, proprietary systems that have fixed it, but the fix for it is kind of foundational. You actually have to redesign the whole database. instead of one write-ahead log, you need two. It's a lot of stuff you need to do to start actually having like it's called a storage fault model. So most databases have like a power loss model. Can we pull the plug?
Right.
A storage fault model is a lot harder because you have to assume. So the SQLite docs will say this. SQLite assumes that data it reads from disk is the same as what it wrote. But with physical disks, that's actually researchers today like that's not true. And the probabilities around this stuff are actually, they're not that rare. So you're looking at, a 2-year period with a few disks, you're going to be having these events. But you'll never know unless you have software that knows to detect them and repair. Otherwise, it's just, your photo is going to get a little bit 1970s effect. One pixel will flip colors, but you kind of need file systems like ZFS. And I think this is what I was always excited about, Aaron, is like file system stuff is so advanced here. Like ZFS solved this stuff years ago, but somehow we went interdisciplinary in our database work. So all the cool file system stuff, the RAID stuff, RAID can do stuff like, if a 1 meg chunk got corrupt, just re-replicate that. In distributed systems today, it's like we got a 1 meg, thing on our database node corrupt, throw the whole node away and re-replicate like terabytes. That's the consensus approach. And you're like, why don't we just learn from like ZFS and RAID? And so, yeah, protocol-aware recovery. These are all the techniques we brought into Tiger Beetle. So you can actually, so Carl Kingsbury of Jepson, he wrote a report on this. He was corrupting every single node in the Tiger Beetle cluster simultaneously. Like he's doing, the thing where you have a cluster of 3 cups on the table, and you put your data under the cup, and then you move the cups around. And he was doing that to the data, like literally taking valid parts of the database and in the file and moving them. So now the checksums look like they're still correct, but they're in the wrong place. And you're doing this, and then he's still trying to see, can he break strict serializability, but he couldn't. He did find one correctness bug in our query engine on the read path, and we fixed that right away. That was a very cool bug that he found. But yeah, normally, like you could never do this kind of stuff. We just had a methodology, like the philosophy we use is Tiger style with the DST, the simulation testing. That was the only way we could have tried to, because normally just to solve network fault model and Jepson and strict serializability is impossible to solve. Like almost every database, he breaks it. But with a DST, you can start to survive the network fault model, like crashes and partitions. But it's also now you've got like a safety rope. You can climb the mountain safely. You're not free climbing anymore. Now you can also like take on much harder, tougher protocols like storage fault tolerance. So now you can also have the cups moving around. Someone's messing with your data files. And you can still climb the mountain because the simulator just makes it so much easier. So we like code on Tiger Beetle. Our simulator is called the Whopper after War Games movie. War Games has got the Whopper, and ours is called the Whopper, View Stamped Operation Replicator. And you're just coding stuff, and you run the simulator. It simulates like. So we actually have 1,000 CPU cores in Finland with Hetzner. They run simulators 24/7. Roughly, very roughly, because it changes, but that adds up to about 2,000 years of simulation time, because we're ticking time in a wild true loop. It's a 700x speed up factor that we've worked out. And so you contributing open source to Tiger Beetle, you put your PR in, it gets fuzzed on this fleet, and after a day, you haven't got 30 years of confidence, you've now got a few centuries, and because you have to like think differently. Otherwise, the central bank switch is not going to use it. But now with Tiger Beetle, now they're like, nervous. Now there's questions like, but what about our queuing infrastructure? Like we should do some DST there, or, all our other systems. And that's sort of what you can't be as safe as 30-year-old tried and tested. You've got to, but I think that's the long story here, is that a lot of safety techniques, there's so much that we can learn from research and testing, and so that was why I was so excited with Tiger Beetle, because I thought, wow, here's an opportunity, and like, you could actually, now we can go and do this. We can learn from ZFS, and so, yeah.
So. I love how basically every every question I ask, you're like, oh, there's a paper, and you can rattle off the name of the paper like off the top of your head, and the authors, and you're very clearly like deep into the research and the literature, which I think is probably pretty rare if I had to guess. And this is now the second time I've heard about deterministic simulation testing. The first was Glauber a few weeks ago at Terso with their rewrite. So one of my questions, or I guess a further question, can you explain to me in a way that I would understand when, so like I read, the Backblaze drive failure reports every year because they're so fascinating about all the drives that fail. But like you said, those are like full failures, I think, the power that you mentioned earlier. Like if the drive goes away, what do we do? Like you're describing something different, which is where like, the God particle hits the disk and flips a couple of bits, and now you're hosed, right? Yeah, I don't know exactly what it is that like makes the bits flip, but how do you how do you
or
Brian
Cantrell standing next to the server shouting? I don't know if you've seen that video, because that can also flip the bits. That Brian, his powerful voice.
Oh, that's incredible. So how do you like? What is the 101, the high level of? How do we detect that just a little bit of this disk went bad, or like these bits were flipped, and how do we recover from that? Like what's the intro explanation for how you ensure that doesn't make it anywhere outside of its little area?
So I think the Backblaze reports, they might show you, if you look at the smart stats there, they will show you like reallocated sectors. That's where the disk internally is seeing that, this CRC thing didn't look good. I'm not going to trust that. If it was spinning Rust, in the old days, then it'll start reallocating sectors. And so it does have partial failures, but for a long time already, if you're running ZFS as a home user and you check your logs, you'll probably see that ZFS is saving you and detecting you from stuff that the disk would otherwise miss. So if you're using XT4, you're vulnerable, but only ZFS would save you here. Or TigerBeetle, but most databases wouldn't. So it would actually come up with a reasonable probability. I've run MySQL in production when corrupt on me. That was when I stopped using MySQL. It was quite a long time ago, but it actually got corrupt, and I was shocked. And that was 10 years before TigerBeetle, and then I was following the storage research for 10 years, and I kept wondering, but why is nobody like listening? And it like the various compartments in research and industry were not cross-pollinating, And so how do we solve it in TigerBeetle? So you have checksums. They're cryptographic checksums, 128-bit. The trick is that you have to daisy chain them. So you're storing the checksums out of band. So the technique is, it's called a copy on write file system. But the trick is that whenever you're going to update some data, you don't update it in place because you might have power loss. So what you do is let's say your disk, just cut your disk up into 1 megabyte little partitions. Just imagine you've got a gigabyte, so you've got 1,000 1 megabyte things. Each one has got a checksum, and then you have some, and then when you want to update 1 meg, in your little grid of blocks, you go to a free slot, you write the new version there. Now you've got two versions, and then every now and then you do something called a checkpoint, where you have a little bit of special metadata called, it's like your root node or your root block. ZFS calls this the Uber block. TigerBeetle calls it the super block. If you look at our repo, the super block code is beautiful. Zig reads a lot like TypeScript. It's very accessible. So you could go and read superblock.zig and see exactly how we do this. But every now and then you checkpoint, and what that does is your in-memory bit set, which tells you which of the 1 meg things are free or used. You update that, and you also write that. You have like 4 copies of the superblock on disk at well-known locations, like at the start, and you update them one by one and now you switch to a new version. And then at startup, you'll see, oh, okay, these are the referenced ones. These are the old ones. Now I can reuse those. So that's how it's a copy and write file system. That's how ZFS works. Tiger Beetle is essentially a file system, can run on raw block device or file system. That's how we do it. And then the checksums are all stored out of band. So the superblock has got special protection and it's replicated locally. And there's very cool techniques that we do in there. A local disk is kind of like a distributed system if you squint. And so you can use the same techniques, quorums, read-write quorums. There's a whole lot of techniques from UW-Madison that we put in Tiger Beetle. ZFS uses some of these. Then you get your root node checksum. That will give you the checksum for more metadata blocks, which have more checksums, and they have pointers to other blocks also with checksums out of band. So that way you can survive when it's totally fine. You know, there was a bug, I think XFS recently had a bug where sometimes it would write your data to the wrong sector and tell you it's okay. It's called a misdirected write. That's 10 times less likely than bit rot. But it happens, and file system bugs cause this, firmware bugs, even hardware. But if you're storing your checksums out of band like this, daisy chaining, think of like a Merkle tree. I think a lot of people will know that. It's the same principle. So long as you protect your root checksum, and that's through your special superblock checkpoint process, you can update that every minute or two. Your database has a write-ahead log, just like other databases do. But yeah, protocol aware also gives more details. Anything there that makes sense?
Everything there. That was a very good explanation. So
cool.
With all these little blocks or they sound like pages, probably like
pages,
they all
pages,
have these. They all have these checksums. What happens if you pick up a page and it doesn't match the checksum? What do you do? Because that's now at least you're in a good spot where you're not going to just play with dirty data, but how do you fix it?
Yeah, so now you actually know. So as a user, you'll start to see, yes, my disks do corrupt, but I now believe that is true because my software can even detect it. So it's kind of like a chicken and egg. People say, disks don't corrupt, but that's because they don't use software that would ever know. So it's like Schrodinger's cat. They never open the box and say they don't know if it's alive or dead. Do cats die? But you have to sometimes open the box, and then anyway. So what happens? And by the way, that example, the 1 meg, Tiger Beetle's pages or block sizes are actually half a meg, 512 kilobytes. Because, a long time ago, you would want 4 kilobytes, but because of how things are changing, the data rates are increasing. You want to move to bigger packet sizes to amortize, again, your syscalls. We use IOU ring as well. But so what happens if we detect a faulty block? So now we know about it. Tiger Beetle's it's a distributed database. It's not horizontally partitioned. It's distributed because it uses consensus replication. Your data is replicated across multiple machines with strict serializability. If the primary goes down, there's automated election or a view change of a new primary, like in a split second. So you have very high availability. You have very high durability. It's like ZFS, but distributed now. And so something goes wrong on one machine, we just go and get that 512 KB block from any of the other replicas, and that replica will ask them. And all of this is tested with DST, fault injection. And that was why Kyle could do this with the replicas and corrupt all of them in different places. But we actively, proactively test this. And the other thing we do is it's not just about do we mostly recover, but people are paying for this. So they're paying, for replication, because now you have your NVMe, you've got 3 disks, you've got 3 machines, you paid for 3. So the principle that we test is, did we lose 1 copy? We must be available. Did we lose 1 copy of an object? Did we lose another copy? We should still be available. And only when we've lost all 3, we must then detect it and shut down and stay down safely. So if there's durability or redundancy, even a shred, we have to stay available. And our simulators, they don't just test for split brain. That's like table stakes. We actually test, are we stretching the available redundancy that you're paying for? Are we turning that into the highest possible availability given all the faults in the system? And we really spent we spent like a whole year just to optimize that stretchy, elastic thing. And so then you're really getting extremely high availability. And for example, Raft and Paxos, if you're losing a majority of copies, they've shut down and broken long ago. So they can't do this. So you have to, we use view-stamped replication, and we bring in all the findings of protocol-aware recovery. And then we've done this work to really stretch it and so it's kind of like a lot of databases, yes, they make backups in real time because they replicate, but they never test the backups. And even if they did, they don't know how to fix them. So you're like, yes, we're making backups, but actually nobody is really testing them. And Tiger Beetle is now, thanks to protocol-aware recovery, we're making backups across the cluster in real time, strict sizability, zero RPO, and then we're also testing them because we're like ZFS, we've got a background scrubber that's like going through your data files. Before your queries come in, we're even checking, because maybe you're not using your cluster too much for a year. Tiger Beetle's continuously checking data that it's okay, self-healing. So it's testing backups, healing them, just like ZFS. We're really not doing anything new. We've just was lucky timing, and we could transplant a lot of learning, and so
dude, this is so fascinating. You're very good at explaining this, by the way. It's very helpful for me.
Thanks, Aaron. I feel like I take forever. I feel like I get slower and slower.
Great. What else are we doing? That's the whole point of being here, is to talk about it. No, it's perfect. So as we finish up, tell me, where is this deployed? Who's using this? What's the structure of the company? Because you keep talking about open source, and so tell me about kind of the shape of the business, who's using it, and how people can get involved.
Cool. Yeah. So I got really excited, when we figured out we could go really fast as an open source project. That's how Tiger Beetle began 5 years ago. And then I also had a feeling that this could change things. And then people in the Gates Foundation project, people said, love the performance, love the safety. Now you've made us nervous about our other systems. We still have a problem. Where's the company to support this? Because people it's not enough. This is sort of took me a while. It was my second moment of enlightenment or something personally, because open source is either too expensive or cheap. So a lot of people are like, I love open source, but it's too cheap. I need to be able to pay someone to come and help me to support it, to run it, or to deploy it. And a lot of startups are like, open source, we love it, but it's too expensive. I can't afford SREs for each database that I run. I just want a push button, run it for me, managed, And so people want to pay. And so open source and business model are orthogonal, I think. And so we to support the database, we founded Tiger Beetle in 2022, 3 years now in next month, our birthday, and that also makes it sustainable. So now we have customers around the world, all over, in the US, in Brazil, in Europe. We signed our first big unicorn recently, Money Farm in Italy, a big multi-billion-dollar wealth management company. So that's a lot of people's assets, all busy moving on to Tiger Beetle. We're doing lots of these projects. The Gates Foundation, that's a national project for Rwanda. Hasn't come out yet, but it's announced, and we're putting it in for that later this year. Energy, company was our first in the UK. But our business is doing really well, so we get customers, they all hit the Amdahl's law limit, ROLOC limit, and they all come, the same experience I had. And they say, look, we would really love nice debit credit primitives, help us. We just want to build our app. We want to build Ticketmaster. We don't want to reinvent transaction processing database. And so, and the team are now 16, a remote company, and we make a technical contribution in open source, and people pay us, and we paid to write Zig and do just keep investing, performance, safety, a nice single static binary experience. And the company it also attracted investment. So We raised 6.4 million in 22, and then we grew quite a lot, like a few times, and were able to raise more investment so we could grow more, and also sustainably, because the revenue is key. So these are all things. Sure. That was actually why I think you and I studied accounting, because it's the language of business around the world. So, that business has been my second love. Coding and business, and so I actually love building a company as much as a database.
Well, it sounds like you're having a lot of fun and a lot of success, which we love to see. So tell people, like, where can they go to learn more about you, about Tiger Beetle, about research papers? Tell anybody, like, give us some links to where we can dive deeper into this stuff and where we can follow you.
Okay, cool. Yeah, so TigerBeetle.com, github.com/TigerBeetle/TigerBeetle. That's the code. I would really recommend also reading Tiger Style, which will show you how to build these really hard systems safer, faster, and in less time. So, we got Tiger Beetle to production in 3.5 years, which is almost unheard of for these tolerances. But again, it's DST. So if you want to learn how to do these techniques yourself, go read Tiger Style, because you can actually apply the same methodology to, and a lot of, like Terso, they're now, Limbo is because they decided, actually, let's throw the whole database we were writing away, let's do Tiger Style. And now they're already ahead quicker. And so, yeah, read Tiger Style. And then the other thing I would really recommend is our YouTube channel. We have Matt Cladd, creator of Rust Analyzer. He's so awesome. He just having calls with him is so great. He works with me on Tiger Beetle, and he has something called Iron Beetle, which we have like 70 episodes now. He's like your guide, and you walk through the open source code for an hour each week. It's live on Twitch, but the episodes are on YouTube. You can catch up 70 hours, and then he takes you through all the design decisions, like how do you build a database, message passing, storage engine, compaction, LSM, consensus.
So cool.
All in detail, like and this concurrency thing we spoke about. There's a whole episode on that for like an hour or two, and so that's Iron Beetle. There's very cool music, metal music in there too. I would recommend that. Like, I've also done a few talks that are a bit shorter. So, yeah, thanks, Joran.
Yeah, of course. My fellow nerds and I will definitely go check that out. That sounds incredible. This has been great. This has been a lot of fun. Tiger Beetle is very impressive, and you have a very nice way of explaining things. Where can people find you on the internet?
So I'm on X quite a bit, and on YouTube. X, Joran Greef. And I always love to chat with people. So we love to just have fun, because we've also been, a lot of doors opened for us. We're really lucky, and it's kind of like, I don't know if you've read Ken Follett, Pillars of the Earth. That book. It's the stonemason. He wanders around medieval England for years. He has this dream of building a cathedral, looks at the forest and the beauty, and but no one can build a cathedral unless you get a patron. And one day he does, and now it's like Sagrada Familia, and he gets to build. And so we were just really, like, people paid it forward to us, and so that's why it's you kind of pinch yourself, because it's so nice to get to build these things as open source, pay it forward. So yeah, people should just reach out. And we've also got Systems Distributed, which is friends of ours that we learn from, and these ideas, talks there. But you'll see us around, and we're pretty. I hope we're friendly folk. So love to chat. Yeah.
Well, thanks again for doing this. We'll leave links to all of the stuff you mentioned down below. They'll be, if you're listening on RSS, it'll be in your player. If it's on YouTube, it should be down below. Thank you all for listening. Joran, thank you for spending an hour and a half with me. This was a delight.
Thank you, Joran. Yeah.
Yeah, absolutely. And if y'all have anybody you want to see on the show, just reach out. I mean, this is just a chance for me to talk to people who are really smart. So if you want to see somebody, reach out, let me know. And until the next time, thanks for listening. See ya.